Hi. Hello.
Hello.
Can you hear
Hello.
me? And can you see me?
Yes.
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 How are you guys?
Fine, and you?
Doing good.
I'm fine too. I hope that you're safe from the COVID and
Yes, for the moment, it's okay
Yes.
for us.
You're
For me.
same for me.
for me too. So we are waiting for Carlos. I hope he's
Yes.
joining now. Mohammad is not joining the class, no?
No, because he have like two
He's
class in
having
the same
another
time,
class.
so
Yeah.
he follows that class with YouTube video.
Okay, okay.
This class is following through YouTube lectures.
Yeah,
So
yeah.
yeah.
I'm recording the class, so at the end of the class, we will upload the video to YouTube. And also we will upload the slides to the group. Okay.
Okay.
Okay. We will give 5 minutes more to Carlos to start.
What is the subject today?
Today we will talk about natural language processing. So we will
Okay.
continue with the first session, but more in depth. So I hope you enjoy it. We have a theoretical part
Yes.
and practical part. Okay. I have some scripts in Python, and we will run together these scripts and see what happens with the text. Okay.
Okay. It's nice because we have seen like other type of NLP with like for genes and something like that with
Mm-hmm.
some dynamic programming for distance errors and things like that. So it's
Yeah.
related to.
I hope you enjoy this class. Okay.
Yes.
Hi, Carlos. I hope we are all so.
Hello, yes, can you hear me?
Yeah, perfectly. How are you?
Hello. Yeah, I'm having some connection problems now, but
Okay.
uh,
So as I said to Robin Abinaya, I'm recording the class, and at the end of the class,
okay.
we will upload the video to the YouTube channel. Um, and also, this class is we are going to go further to the NLP, natural language processing, and this part is theoretical and practical. So I have some scripts in Python, and we will run together, and we will see what's the output of the scripts. Okay.
Perfect. And which library are we using in Python?
I will use NLTK and Spacey and Spacey. Okay. I will use
Uh,
Python 3.8. I don't know if you have it, but you can install meanwhile.
Yes, I
Okay.
have
yeah.
Python to find.
I use 3.8 because other versions, the 3.5 or 3.6, doesn't run the Spacey code. Okay, that's the reason. So uh, I will share. Sorry, I just forgot to share the screen. Give me. Tell me if you can see me in my screen.
Yes, it's working.
Yes.
Okay. So we will start this new session, complex data. As I said, we are talking about further, going a step further to the NLP. So this is the index of contents. First of all, I will talk about what is natural language processing. I will boring you about giving you a bit of a history of NLP. So we are trying to solve the question that why NLP is interesting. I show you some components of the natural language processing. And also I show you the atypical information extraction pipeline and some subtasks that may you carry out. okay, when you use NLP techniques. And also we try to solve the question of why natural language processing is hard. The second part of this session is to apply the NLP techniques in the biomedical domain. I will show you the electronic health records. I give you some characteristics of the biomedical text, some challenge, and also how to extract information from biomedical documents. Okay. So, what is natural language processing? It's a branch of the artificial intelligence that helps computers to understand, interpret, and manipulate human language. Okay. If you have any question, please interrupt me. Okay. So, the born of natural language processing, it's in 1950, even though this natural language processing is mentioned in some texts in the first decade of the 20th century. Okay. In 1950, Alan Turing wrote his paper Computing Machinery and Intelligence, where describes a test called the imitation game, nowadays is known as Turing test. I don't know if you go to the movies or someone, but there is a good movie called The Imitation Game, and it's related with the life of Alan Turing. So I recommend you to watch. I think it is in Netflix, by the way. So Alan Turing is considered as the father of computer science. Okay. In this game, the imitation game, in Turing test, Alan Turing described this test in order to detect if a machine is capable to think like a human being. Okay, and he designed the test where we have a human judge here, and then this judge needs to define if he or she is talking with a machine or another human, okay? And the conversation is using natural language, but written, okay? It's not talk, it's only written. So the judge only knows some characteristics of the opponent, for example, the age, okay? In order to know the degree of expertise of the opponent, okay? Alan Turing thought that this test will be passed in the early 21st century. But until 2014, there is no an artificial intelligence or machine, okay, that passed this test. It's called Eugene Gustman, okay? But here we have dilemma, okay? Because we can a machine or pass this Alan Turing, it really have the particularity to think like a human being or not, or it's only capable to retrieve the important information from the text and call the internet and retrieve the most accurate answer to that question. Okay, this is a controversial here if the machines think like a human or only think because they are capable to extract information and talk to internet and retrieve the correct answer. Okay. So in 1952, here is the Hodgkin-Huxley model. So how the brain uses neurons in forming an electrical network. Okay, here you have the Hodgkin-Huxley model. I will now go further here, but with this imitation game, with this appearance of the Turing test, and in particular the paper of computing machinery and intelligence, and the publication of Hodgkin-Huxley model, these events help to inspire the idea of the artificial intelligence, the natural language processing, and the evolution of computers. Okay. In natural language processing, we have three main steps. The first step is the symbolic natural language processing, is during 50s and the early 90s. Okay. In 1954, there was developed an experiment called the Georgetown experiment, because it was developed in the Georgetown University. And here the researchers were capable to translate more than 60 Russian sentences into English. Okay, they thought that this automatic translation task will be solved in 3 years. Okay, but it's nowadays it's an open problem. Okay. In the 60s appear systems that works in restricted words with restricted vocabulary. For example, this one, and Eliza. Here you have an URL of Eliza. You can talk to Eliza. I show you the demo. How this is Eliza. It's a program that emulates a Rogerian psychotherapist. And in order to take the illusion of intelligence, you have to limit your conversation to talk in order to talk about yourself and your life, like this appear here. So here, hello, for example, hello, how are you? And Elisa, I hope she, okay, would you prefer if I were not? So if you go, in other type of vocabulary, Eliza start to retrieve some strange answers, okay? For example, so because I talk about myself, she answered properly, okay? But if you go outside this vocabulary, Eliza starts to give you some strange answers, okay? So in the
that was the first chatbot, I think.
No, the first chatbot considered chatbot was Parry. It's in the 70s, okay? It's
Okay.
It's the first step to build a chat, okay? A chatterbot, okay? But it's not considered as a chatterbot, okay? It's starting, but it's not considered as a chatterbot, okay? The first chatterbot is Parry. It was developed in the 70s, and we will talk with Parry now. Okay, I show you a demo of Parry. So in the 70s, started to develop of conceptual ontologies, which structure the real-world information into computer understandable data. Okay, the first ontologies were Margie and Sam, and Robin think answer. This is the question to your. This is the answer to your question. Sorry, this is Parry. This is the first chatterbot. Consider the first chatterbot is try to simulate a paranoid schizophrenic. Okay, I don't know what happens during the 60s and the 70s with this obsession with.
Welcome to Botlieber.
Sorry, the session was. Okay, you have to go. It's not my real birthday, okay? This is Parry, and you can talk to him.
It's about time you showed some interest in my feelings.
So you can chat with Parry if you want, okay? It is only to show you how it works. And you know Parry. And during the 80s and the early 90s, the research goes to the rule-based parsers, which huge handcraft rules. He started to show interest in the morphology of the text, the semantics of the text, and some reference and other areas of the natural language understanding. Okay. So the second stage of the natural language processing came with the 90s and the first decade of the 21st century. Okay. In the 90s, we have success in statistical methods occur in the machine translation, okay? If you think about the experiment of Georgetown, where the researchers thought that in three years it was machine translation will be solved, but here in the 90s is it's an interesting field too in machine translation, and also in nowadays is an open field, machine translation. Okay. So these statistical methods are capable to take advantage of multilingual corpora. So we have data sets. If you remember the data set for the first session, it's data labeled manually for humans. Okay, and we have the data set in English, Spanish, French, German, etc. So these systems take advantage of these multilingual datasets in order to perform better machine translations. The limitation is clear. The system depends on this corpus, and this corpus needs to be specifically developed for the task. So also in the 90s started to have a great impact of a great research interest in effective methods using limited data. In the 21st century, with the growth of internet, we have a huge amount of unannotated data. So the research here increasingly focus on unsupervised and semi-supervised algorithms. Unsupervised algorithms are those algorithms that detect patterns in unannotated data. Okay, they not use labels. They use only the raw data, and they are capable to detect these patterns. Okay, and semi-supervised algorithms have a little amount of label data and huge amount of unannotated data for the training. Okay, so they use the annotated data to create a first model and divide the unannotated data into batches. Okay, so they use the first batch with the first model trained with the annotated data, and they annotate this unannotated data, okay, according to the previous knowledge. So once they annotated by the machine, okay, not by humans, only the machines with the previous knowledge. So once they have the annotated data, this new annotated, once they have this unannotated data labeled by them, they include it in the corpus, in the data set, and use this new corpus to retrain themselves and create a better models. And then we have a new model, and we use other parts of the annotated data, and so on. Okay. The last stage of natural language processing is the present, and here we use deep learning methods. And these deep learning methods achieve state-of-the-art results in many tasks of natural language processing. We have language modeling, parsing, etc. Okay, this is an example of not the last, but the latest deep learning method. It's GPT-3, and I show you a demo of this GPT-3, and you can see by yourself how powerful are these deep learning methods. So
GPT-3 is like used for a lot of things now.
Yeah, it's not publicly released. It's but you can specify in natural language some task to perform, and with that description, GPT-3 is capable to perform that task. So this
okay,
is
so
yes.
it's like a shell or an algorithm, or I don't know.
It's
I don't see what is it.
So it's only you have in deep learning you have some methods. Okay, you have the neural networks, for example, LSTM, long short-term memory. You have recurrent neural networks. Okay, so in the latest year became some, for example, Google started to create their own model It's called BERT. I don't know if you know it. BERT.
No,
BERT. It's a model developed by Google, which a huge amount of data can perform a lot of tasks in natural language processing. For example, name entity recognition, sentence extraction, etc., etc. And it's quite popular because it go further from the state of the art. But it's only a model, okay? This is one model, BERT, and this year the OpenAI developed a new model. It's called GPT-3. This is the GPT-3. It's have more parameters, like I think it's like 13 billion parameters. So in order to train, you need more and more data, but these companies have all the data in the world because it's Google, it's Elon Musk, okay, so they have all the data in the world. So with all this data, they achieve great results, okay? But GPT-3, BERT, or other are only models, okay, that are trained for a task and perform that task, okay? I don't know if it's clear.
Yes. Do you need like a lot of data if you want to train your model, or you can do?
Usually, when you use BERT or GPT-3, you don't retrain that model. You because it's impossible for us, for the researchers, the common researchers, to have that quantity of information. Okay, the access to the quantity of information.
Yes.
So you do you extend the behavior of that models. Okay, instead of retrain from zero, you have the previous knowledge and you extend the knowledge with the data and the task that you want to perform. Okay?
Okay. Thanks.
You're welcome. So this is the demo of GPT-3. Okay. Here the researcher write something to design an app to GPT-3. So he wants, I don't know what happens. Sorry. This is the specification. He wants an app that has a navigation bar with a camera icon, with a photos title. So with this description, the system it's capable to create the app with the whole code and so on, with that tiny text.
Yes, incredible.
It's
but
really
a little bit looks like an Instagram.
yeah, it's like Instagram, okay? The artificial intelligence, the model, in a matter of seconds, design Instagram with a short text. It's I think it's really cool. But what OpenAI achieved with this model, I don't know about your opinions, but that's crazy. Okay, I think it's crazy to what it's achieved in the natural language processing field in this year, because GPT-3 is from this year.
Yeah, I never saw something like that in natural language processing. I saw more bioinformatics reading of records and something like that, and other information, but not in the opposite side like this one. It's the first time.
Yeah. And you have GPT-3. It's if you see these demos, you have this is one of them, but you have a bunch of tasks, and it's really incredible what they achieve with this model. Okay, but unfortunately, GPT-3 it's not publicly available. Okay, so this is the history from the very beginning of the 50s to the present. So now we are trying to solve the question why NLP is important. Okay, if you see this picture, this picture shows how much data is generated every minute. Okay, in this case of 2020, every minute of the date, but you have these statistics from 2019, 2018, etc., etc. So as you can see, every minute in the whole world, 42 almost 42 million WhatsApp are written in the whole world. In Facebook, the users upload like 147,000 photographs per minute. Okay, and this is crazy. This is really crazy. A human being, I think the entire race of the human beings can't handle these volumes of data. So why NLP is important? It's important from the perspective of the text. Okay, it's important because it can handle these large volumes of text data and retrieve in a matter of minutes in some answers. Okay, good or bad, but they are answers. Okay, and the NLP is also important because they structure highly unstructured data sources. If you remember the first class, for example, the text that are in the documents or PDFs is unstructured from the point of view of the computer. Okay, and here with the techniques of natural language processing, we are going to obtain the most important, or we try to obtain the most important data from this text and structure and save this information into databases, and we will have the structured information, and it's easier from the point of view of a computer to process this structured data. Okay. Where we used NLP techniques, for example, in the chatterbox, for example, Siri. Siri is capable to understand what are you talking and retrieve the most accurate information from your question. Okay. Also, from the translation, the machine translation, we used the NLP techniques. And also in the Netflix, for example, there's a task called so the recommendation system. Sorry, we have a task to recommend videos or series according to your taste, also according to the taste or the behavior that other users, the most similar users, have. So, for example, if you have some interest in some particular kind of videos, and there is another user that have the same behavior as you, and also saw some videos or some movies that you didn't watch, so they recommend those videos. Okay, the Netflix system is capable to recommend the videos to you. So, components of the natural language processing. Okay, we have the input sentence of the input text. Okay, first we go through the morphological processing, morphological and lexical analysis. Here we want to analyze, identify, and describe the structure of the words. So the text here is divided into paragraphs, paragraphs into sentences, and sentences into words. Okay. Once we have the words, we go through the syntax analysis. Yes? Oh. Syntax analysis.
Hi, I'm Dave Robinson. I work at Stack Overflow, and I'm going to be talking about GG Animate.
Sorry, I leave this on, okay? So the syntax analysis identifies the syntactic structure of the text and the dependency between the words that are in the text. So here we use the lexicon, vocabulary, and external grammar, okay? The third step is the semantic analysis. The text is checked for meaningfulness. Here we use semantic rules to perform this semantic analysis. And finally, we have the pragmatic analysis, the focus on taking a structured set of text and figuring out what the actual meaning of the text is, okay? This is more related with linguistics, okay? This is more related with linguistics than the, well, it's because the NLP, we have the part of computer science and the linguistics side, okay? So it's more related with linguistics than computer science, even though it's related. So we are going to go to the scripts now, to the practical part. This is the pipeline that we want to create. So we want to have the raw text is in a string. We want to separate the text into sentences, then the sentences into tokens or words, okay? With these tokens, we are going to perform the part speech tagging. It's to assign grammatical types to each word. And then we are going to detect the entities and the relation between entities, okay? So the first subtask is the sentence segmentation. Sentence segmentation is used to break out the whole text into sentences. For example, we have the text, "Hello everyone, nice to meet you." And we perform this sentence segmentation and we have two sentences. "Hello everyone and nice to meet you." Okay? So this is your part, okay? I will share with you this whole text, which is extracted from the King Henry IV, written by William Shakespeare. So we try to give me set. This is the text, okay, you can copy it. Okay. And you are going to write or rewrite this whole this script. Please run it in your machine and talk to me. Please, if you use this sentence tokenizer for the first time, you have to uncomment this line, the nltk.download punct, in order to run the code. So please run it and see what happens.
Can you make a little bit zoom on the text, please? Yes. Nice, thank you.
You're welcome. I will try to run the code also. These libraries is for general purpose, so maybe the results that we obtain here are not that the expected one, okay? But it's only to a demo in order to enlighten you what is this task, okay? So were you capable to run this code?
I don't know. I download the file for the package. And that seems okay.
I'm just finishing to write the code.
Yeah. Maybe take a while because it needs to download the punct.
It's working for me too.
So what is your output?
Let's see. So it's given. Is this a list?
We have.
Yes, it's given
yeah.
like a list of sentences.
Yeah. We have
Yes.
break up the text into sentences. Okay. So, congratulations. You have performed the first task in our pipeline is to break up the text into sentences. Okay. The second part is the part of tokenization. It's the same as sentence segmentation, so instead to break up the whole string into sentences, we break up into units called tokens. Okay, could be tokens could be words or punctuation marks. Okay, so in this case, nice to meet you. It will be with the word tokenizer. We have nice to meet and you. Okay. Also, there is
I have a question.
Yeah. Okay.
What is the definition of token? What is a token?
Okay, I don't have. Yes, I will search the definition, the token definition, but to give you more precise definition, okay. But if you Google it, you can find the definition. But okay, that's okay. I didn't mention it, the definition here of token, but I will share with you at the end of the class the definition of what is a token. Okay.
Thank you.
But
Okay.
it's only for you only to have an idea. Tokens are words. Here also are the punctuation marks. Okay, are considered as tokens. Okay, but sorry, I give you the definition of what is a token once we finish the class. Okay.
I sent a definition I find on Google.
Yeah.
I don't know if it's good or not. But...
maybe it's a good definition, okay? But I will find the definition and I will share with you at the end of the class. That's a good question, and sorry for not to have a definition of what is a token, okay? So the second example here is the same. We have the same text. Instead of using send tokenize, we will use word tokenize. Okay, we can tokenize the text directly, or we can perform the sentence segmentation and then the word tokenizer. Okay, the output is the same. Okay, we have the same tokens, but the output differs. That in this case, okay, first run this program, please, and I'll show you the difference between first segment the sentences and then apply the word tokenizer. Okay. and tell me once you run the code what is the output of the script. Okay.
Okay.
Yeah.
We have
Yeah.
just plenty of words written.
Yeah. So as you can see, how many tokens did you find?
141.
Okay. And what are your tokens? Words? Only words?
Yes, I think it's all word. Ah, no, I have comma and dot too.
Okay. As you can see, you have a list of the different tokens in the text. Okay. In this case, a list of 131 tokens in my case. Okay. And it's, as you can see, you have words, you have punctuation marks, last the comma, question marks, etc., etc. Okay.
So it's essentially everything except the white spaces.
Yes. Okay.
Okay.
This is the tokenize all the tokens except the white spaces. Okay. In this third example, we are going to mix the sentence tokenizer and the word tokenizer. Okay. First, we apply the sentence tokenizer, and for each sentence, will apply the word tokenizer. Okay. And you will see that the output is, as the words found here are the same as in the previous case, in example number 2, but it has a different output, okay? Or the way that it shows the output, okay? Please run the code and tell me what is your output here.
Okay, for me, the output is like the sentence followed by word token.
Yeah. So
The
here,
sentence.
yeah, you have
Yes.
the sentences and a list of tokens of that sentence. So if you instead of print the sentence and the tokens, you print directly the whole tokens instead of having this list of tokens that in the previous case we will have a list of tokens, 2 lists, okay? Where the second list is represents the sentences, okay? So as you can see, the output, the tokens detected are the same, but the way that the output looks like it's different. In the first case, we have only a list, and in the second case, we have a list of lists. Okay. So we will continue with our subtask. The second subtask is this is optional. Okay. It depends on the task that you are going to perform. For example, if you are going to perform a classification, okay, to classify a sentence into, for example, you have a sentence and you have to classify this sentence if the person is a smoker or no smoker, okay? For this kind of task, it's a good choice to remove the stop words, okay, because they don't add a semantic value to the sentence. But for example, if you are going to perform to create a new text from the input text, create a new text, okay, it's not a good idea to remove the stop words because the output will be something strange. Okay, if you read it without these stop words, it's something strange. Okay, so you have to keep in mind the task that you are going to perform in order to remove or not the stop words. So the stop words are high frequency words that add little or not semantic value to the sentence. For example, which, to, at, for, etc. They are different from one language to another. And in the same language, depend on the library that you are using. These stop words are different. Okay. So this is an example. The original text is: some simple sentences have a single subject and verb, but the subject is in a state in the sentence. If we remove the stop words, the text is shorter, but it's like something strange. Some simple sentences, single subject, verb, subject, stated sentence. It's something. If you read it in out loud, it's something strange. Okay. So, as I said, depending on the task that you are performing, for example, classification task, is a good idea to remove the stop words, but in text generation is not such a good idea, okay? So this is the fourth example. Here we are going to remove the stop words from our text, okay? So, please copy and run your example and tell me what is your output. First, you have to download this nltk.download stop words. Okay. So, did you run the code? Yeah.
Not I. It's just a problem.
What's your problem?
With stop words, but I don't know it. I will try. I just have a message error, but
Okay. Here, I will explain the code. Here, we use the stop words in English from this NLTK corpus, but here I use this stop word that is a set. That means that only the stop word only appears one time here in the set, okay? Maybe it's because I use this. Maybe you have the problem. I don't know.
For me, it's working.
Okay.
Okay.
Yep.
What's the output, Carlos?
It says, well, text without stop words, and it says here, dear, true industrious friend,
Okay.
Sir Walter Bloom. Yeah, so for example, is removed, true. So
Yeah.
what else? Yeah, that those words are removed.
So
From
if you read,
Connectives.
yes, Abhinaya, sorry.
No, the connectives and words are removed, like on and off.
Here
some verbs.
at the
Yeah.
beginning, you have these stop words. I print the stop words used that this NLTK library used, and you can see that this is the words that we are going to remove from our text if they are in the text. Okay, it's I, me, my, myself, we, our, ours, etc., etc. Okay. So if we detect a word that's in this list of stop words, we remove from the text. Okay. So if you see the final output, you can see that it's the text without these stop words. And if you read it out loud, you see that okay, I understand the text, but it's something strange. Okay. Because these stop words connect the ideas in the text. Okay, as I said, depending on the task, you want to remove these stop words or you want to keep it. Okay, because as I said, if you want to create a new text, generate text, these stop words are essential because they connect the ideas in the text. Okay, but if you only want to perform classification problems, these stop words they don't add value to the text. Okay, so you can remove it and maybe you have better results and better performance on your algorithm. Okay, from here it's okay.
Yes.
Okay, so this is the second optional subtask. Okay, it's called lemmatization and stemming. Here in the natural language processing, we can came across situations where two or more words have a common syntactic root. Okay, because these words are inflected, we call it inflected. It has different grammatical forms. For example, agreed, agreeing, agreeable have the same root. It's agree. Okay, so sometimes, depending on the task, also it becomes essential to link these lemmas or these stemmings to these words to the same root. Okay, so we have two options here. The first one is the stemming. That means to reduce the words, the inflected words, into its root and mapping the group of words into the same stem. Okay, but the problem here is that stemming or the stems produced are not always in the vocabulary. Okay, for example, we have this text. Some simple sentences have a single subject and verb, but the subject isn't stated in the sentence. So we perform the stemming step we have some simple sentence. So as you can see, these stems, okay, the root, the syntactic root of the word are not always in the English vocabulary in this case, okay? Simp is not existing in the English vocabulary, or is not existing in the English vocabulary. So sometimes these stems, as I said, are not existing in the vocabulary. And lemmatization is similar to the stemming, but it brings the context to the words. So it goes a step further from the stemming. For example, if we have words like car, automobile, or train, lemmatization we will capable to link to a new word. In this case, automobile, car, automobile, and train have the same lemma, which is automobile. Okay. And in this case, the root of the lemma is always in the vocabulary. Okay. So in this text, in this original text, we apply the lemmatization. So we have some simple sentences. We have sentence in singular. Have a single subject and verb. But the subject, instead of be isn't, we have be plus not. Stated, it's in the state in the sentence, okay? So in this case, the lemmas are always in the vocabulary. The problem to use lemmatization and stemming is they can mess up with the performance of your algorithm. So you are going to use lemmatization and stemming when you want to improve your recall. Recall means that you want to retrieve as much concepts as possible from the text. Okay. But you want to improve the recall instead of improving the precision. That means that the concepts that you are retrieve are the real ones, okay? So we are going to perform these stemming and lemmatization steps, okay? So in this case, we are going to apply the stemming part. They are different stemmers. They are good in some cases and bad for some cases. For example, Porter stemmer, Snowball stemmer, or Levin's stemmer. Okay, depending of the strength, you want to use one or another. Okay, but in this case, we use Porter stemmer. Okay, it's a well-known stemmer in the state of the art. So please copy and run the script and tell me what is the output.
Okay, so it gives the stem for each word in the sentence.
Yeah.
For example, stem for here is here, but with lowercase.
Yeah.
Well, I don't know. For example, here it says stem for is.
Is
Shouldn't
yes.
shouldn't that be like the verb, like be, for example, like the original
This
form?
the original form will be in. It should be in the lemma, not the stem.
Ah,
Okay.
okay, right, correct. Yeah.
Okay.
Okay.
For example,
Yep.
if you this stem is industrious, it's retrieving industry with an I instead of
Correct.
a Y. If you can see.
All right. Yes.
All right. As I said, sometimes the stems that we retrieve are not in the vocabulary. In this case, in English vocabulary. Or for example, horse. Instead of the stem is horse without the e, the final e. So I don't know in English, but I think it's not exist horse, HORS. Variation is varied. Okay. So yeah, you have performed the stem, but these stems in some cases are not in the vocabulary. So as this, then you have this example number 6. This is the lemmatizer. Okay. Here I use a WordNet lemmatizer. There are other lemmatizers in the state of the art, and please run it. So what is your output if you run the script?
I just need to download WordNet.
Ah, okay. Maybe it take a
That's all.
while with the WordNet.
Yeah. So what had the scene?
I'll give you couple minutes more. Okay.
Okay, I have it now, but I don't know. Still, I see lemma for. Ah, no, sorry. Yeah, lemma for is. For
Yeah,
example, is that correct? Or
it should
lemma
be
for
it should
yeah,
be instead of is.
yeah.
This it's a wrong answer from the tool. Also, you have to keep in mind that these tools in natural language processing not are not always 100% accurate. Okay, they made mistakes. So I think it's a mistake of the tool because the lemma for is should be instead of is. Okay, the stem is from for is. Sorry, that is something strange. But for the lemma should be a be instead of is. So maybe this lematizer is not 100% accurate. Okay.
Actually, I was having a look, and all seem the same. I don't see any changes from
Yes.
one to the other. I got at the first look.
So there is some. Okay, I will show you this. You can okay. This is not necessary for you to copy. And here we are going to compare the. I will try to show you the comparison between the stemmer and the lemmaticizer. Give me a moment. A moment. So can you see the screen?
Yes.
Yes,
So for
yes.
example,
Yes.
industrious, the lemma is industrious, but the stem is industry. Okay. In this case, the lemma should be instead of is, but there is a wrong answer here. For example, lighted, it's light. It should be light. I don't know why, but it's have a wrong answers here. This lemmatizer. Horse is horse, and the stem is horse without the final e. Okay, there are some or variation is variant stem, and lemma is variation. Okay, so you can see there is at the first sight there is you cannot distinguish between the lemma and the stem, but if you take a look deeper, you can see that there are differences between the lemma and the stem. For example, this, the lemma is this, and the stem is D without the final S. Ours, ours. So there are some differences. Not too much, but some quite. Okay. So, do you have any questions from this part? Or can
No,
we?
it seems clear.
Okay. So I will continue. So from this pipeline, we have performed the first two boxes, sentence segmentation and tokenization. Okay. So we are going to perform the third box. This part of speech tagging. The part of speech is to add to each token its semantic category. Okay. For example, if the token is a verb, an adjective, a punctuation mark, noun, etc. Okay. So in this case, hello everyone, nice to meet you. I use part of speech. I obtain that everyone is a noun, nice is an adjective, meet is a verb, and you is a pronoun. Okay. Not always all the tokens are related with its semantic category. Okay, depends on the part of a speech tagger that we use. Okay, but sometimes we don't obtain results for all the tags. for all the tokens, okay? That depends. So this is the part of a speech, okay? This is the script. Please run it. And we will obtain the part of a speech tagging, okay? So did you have output, or it's downloading the average perceptron tagger? Or?
I have an output.
Yeah?
Yes. So I have a list
Yeah?
of tuples.
Yeah?
And one is, for example, here with RB is with VBZ A PT.
These are, if you can see my screen, here is the meaning of the tags. For example, for here, that's RB, it's an adverb, okay?
Okay.
Is a verb, sorry, is a verb in the third person of singular, okay? This is the, I will try to share with you these scripts once we finish this session. So here in the script I posted the source where I obtained the tags and also the definition of each tag, okay? So here we have the adverb is as I said, a verb in third person of singular. A is determiner, et, dr is a noun, comma, determiner. This is JJ is an adjective. industrious is another adjective, friend is a noun, etc. This NP is a proper noun, for example. His is a possessive pronoun. Okay. So as you can see, we have plenty semantic types for our words, for our tokens. Okay. So as you can see, we assign for each token its semantic category. Okay. This semantic category is not predefined. Okay. It's given by the post tagger. Okay. I don't know if you have any question from here.
Can we get that list from Python too? Is there a way, maybe a command to get the meanings?
Yeah,
are there? Okay, are there in the web page, right?
Here
Okay.
I have the web page. Okay, I will share it in the chat. Give me a moment. Okay. Now here you have the definition of the tags. Okay.
Okay, thank you.
You're welcome. So once we have the part of speech tagging, we went to detect the entities. We perform the so-called name entity recognition. So here we want to search, locate, and classify predefined categories. So as we said, in the part of speech, we cannot predefine these categories. These categories are given. But in the name entity recognition, we can predefine the categories. And we can define person. The most common are person, organization, places, temporal expression, etc. But we can define our own entities. For example, drugs, treatments, toxicities, dates, etc. etc. Okay. So in this case, we have this sentence: Michael Jordan is a professor at Berkeley, and the name entity recognizer gives us Michael Jordan as a person and Berkeley as a location. Okay. So we are going to perform also our name entity recognizer. Okay. In this case, the name entity recognizer only recognize these parts: or an organization, person, the name of person, location, dates, time, the money, percent, the facility, the name of the facility, and geopolitical entities. Okay. As I said, you can train your own model in order to detect other entities. Okay. So here, please run this example and tell me what are you obtaining. So
Okay, so I get a graphical interface here.
yeah,
Or some.
you have a tree where you have the text And if you look at it, there are some words that are only have the part of a speech tag, for example here, or is, or a, but there are some groups of words that have a different tag. For example, Sir Walter Blunt, you have the tag person. You recognize Sir Walter Blunt as a person entity, okay?
Okay.
Or Stein as a person, or Bedwick's hold on. Okay, as I said, it's not 100% accurate, and some cases maybe hold on is not a person but a location. Here, Earl is detected as an entity of organization entity, or Douglas a geopolitical entity. Okay. Maybe if we create our own recognizer, we obtain better results than using the holomain tool. Okay, but as you can see, there are some tokens or some group of tokens that are located as a special type, as you can see, or they are located as entity, and you have a special tag: person, GPE, organization, etc., etc., etc. Okay. So at the end, it's also is to tag the with a special category the entities that are located in the text. Okay. And finally, once we have the entity detection, we have, as you can see, for the interface, you have a tree, okay, but you can have list of trees if the text is greater, okay, you have more text. Once you have these entities detected, you want to know the relation between the entities, okay. So you have here the last part of our pipeline is the relation extraction. Okay, here we want to extract semantic relationships from a text. So they usually occur between two or more entities of the certain type. For example, we want to relate person with an organization, or person with a location, or person with an organization and location, okay? And fall into a number of semantic categories. For example, we have the relation that relate two persons is married to, or the relation that relates person with an organization is employed by, or lives in. Okay. So in this text, we have Billy Mays that is located as a person entity, and also we have the Tampa. It's located as a city entity. Okay, and we want to know the relation between the person and the city. And we obtain that this relation is the city of death. So you can infer that Billy Mays died in Tampa, okay, from the text. So this is the final script from our pipeline. And here we are going to extract relations, okay, from the text. For example, we want to extract the relation between an organization and a political entity, and the relation between two persons. Okay, and we use this regular expression. We said that the organization is related with the of relationship, and two persons are related with the relation that. Okay, so please copy the code and see what happens. You can also define your own patterns to your own relationships, okay? But this is only for the example to enlighten the idea. So did you run it?
That's it.
So
Yes, I have it now.
yeah,
Yes.
you have the relations, don't you?
Yes, but so how does it work exactly? I'm trying to get. So I get the word, for example, here slash RB, and then
Yeah, you have the
okay, it's only for names, right?
yeah,
For
yeah, okay.
okay, right. Yeah, well,
You
sure.
you will extract the entities, the names in this case, and you have that Earl, for example, it's an organization, and it's related with other names, in this case Douglas, Fifth, or Athol, that are geopolitical entities with the relation of, don't you? And
Okay,
also,
yes, I got that.
okay, and you have person Bedwix that is related with Holmdon. In this case, it is a person, but I think it's a location, but okay, with the relation that. So I obtain these relations if use watching this the text. Okay, in this case, this is instead of view the user interface like I did before with the post tagging. Okay, this is the post tagging, and this is the post tagging plus the name entity recognizer. So we have that we locate person Bedwix with is a proper noun, another person is hold on is a proper noun, and you can see that in between them we have that. Okay, we can define, as I said, other relations, but I choose these ones. Okay, so you can see that we obtain these relations from the text. Okay. Yes. Questions? No? So with the relation extraction, we have achieved our pipeline. Okay? We have segmented our sentences, the text in sentences. We have tokenized the sentences and the raw text. We have performed our part of speech tagging. We have detected entities, and we have connect entities with relations. Okay. So well done, guys. But it's not over. So continuing with the presentation, why NLP is hard? NLP is hard due to the very nature of the human language. Okay. There are rules that dictate how pass information in natural language are not easy to understand for computers. For example, sarcastic language. When you say something that means the opposite, okay. For example, if you are talking with other person and if this person talk to you with something sarcastic, you infer this sarcasm with the pose or the tone of how he or she talk to you, okay. But a machine don't have this extra information. So it's really hard for a machine to detect this sarcasm. Okay? For example, really, Sherlock? No, you are clever. In this case, if a machine has to detect the sentiment of these sentences, it will be classified these sentences as something positive because it's clever. Clever, it's a positive word, so this entire sentence is positive. But no, it's not positive. It's something negative. Okay. Other rule that is difficult to understand for computers are the plurals, because the different ways that we build the plurals. Windows with an S, final S, boxes, and in Spanish depends of is a female or male, etc., etc. So it's difficult for a computer to distinguish the plurals. Also, the ambiguity in the text. In this case, we have Sarah gave a bath to her dog wearing a pink t-shirt. Okay? From the computer perspective, who is wearing the t-shirt? Sarah or her dog? So this is our difficult task for a computer to from the perspective of a computer, and it's hard to solve for the NLP field. Okay. So here we have to understand human language requires understand the words and how are connected the concepts to deliver the message. Okay, and for a computer it's not easy. So in this case, humans can easily master a language, but not machines. So this is the second part of this session. It's the use of techniques, NLP techniques in the biomedical domain. So texts that are talking about medical and molecular biology. Okay. And first, I will talk about the electronic health records. The electronic health records are the digital version of the patient's paper chart. Okay. They are focused on the patient, specimen center, and information is available instantaneously. So it's in the real time. Okay. And also have another characteristic is to access electronic health records, you have to need some secure authorization, okay? Because in the electronic health record are sensitive information. The electronic health records may contain medical and treatment histories of the patient, diagnosis, medications, treatment plans, immunization, dates, allergies, radiology image, laboratory and test results. So, as you can see, it's very sensitive information from the patients. The tools used here to see the electronic health records are used in order to make the decision easier for the clinicians. Okay, so they have all the information in the screen, and they make this information is used to make their decision easier. It's not to substitute the clinicians, okay? So this is how an electronic record looks like. Here we have for example, the photography of the patient, the name, the last name, the day, birth date. We have the appointment, and for each appointment we can have different forms, and each form has different sheets, okay? It's like neurologic, vascular, cardiac, abdominal, etc., etc. The meetings, the appointment, diagnosis, etc. Notes, and the doctor, okay? So the information that is screened is, for example, in the digestives, is in the digestive inspection, if it's normal or has any problem. From the liver, so some auscultation or other digestive palpation. For example, here we have a little pain on the right lower area. So we have, in this case, an image, and where it's supposed to be the pain. And for example, if we have some radiology results, here we have the radiology results, okay? Some characteristics of the biomedical text is the terms used are not a top priority in general domains, okay? When you write on Twitter, probably you won't publish if you have diabetes or leukemia, or you are using lithium or insulin, etc. So this information that is more valuable to find from the biomedical perspective, okay, has little redundancy. It means that in the text only appears 1 or 2 times, okay? But it's so this complicates the way to locate the important information, okay? We have more complex linguistic phenomena. For example, in the general domain, we can extract a binary relation between a person, an organization, etc. usually, okay? And the terms usually are in the same sentence. But in the biomedical domains, we have relations between several terms. That means we have relation between, for example, a disease, genes, date, cells, etc., etc. Okay, and this and the terms could appear in any part of the text, not only in the same sentence. Okay, so you have to keep in mind how to relate different terms from different parts of the text. It's not an easy task. Okay. Another problem in the biomedical text is the data. If you are using supervised algorithms, you need labeled data. You need data to train your model. But it's very difficult to find examples publicly available due to the nature of the text. It's very sensitive information, so there are protection data laws. So it's really difficult to find examples. So the challenge here for your NLP system, it's you have to have good performance. So you have to, the system is used to improve the quality of clinical care and facilitate the research. So before to use or develop an NLP process, please you have to measure the adequacy of using this process to the task. Okay. You have to recover implicit information. In many health records, you have implicit information that is inferred or is assumed by other clinicians. But your NLP systems here should recover as much as information as possible in order to capture this implicit information. Okay. Interoperability. That means that these systems are has to be integrated with other systems in the clinical institutions. So you have to generate usable outputs that are used to other components. Other is interoperability. You have to exchange data between different institutions, not only with your institution, but with other institutions. You have to keep in mind that there are no standardized language currently. So every institution use their own language, their own reports. So it's very difficult to create a generalistic NLP system. And the model is to be understandable in order to be used the output for other institutions. Okay. As I said before, the training set development, due to the nature of the data that you are using, usually are not publicly available. These documents. So, and the majority of the researchers has not ties with the clinical institution. So it's difficult to obtain these sets of documents to improve your system. Okay. Also, the evaluation is critical in NLP, not in the biomedical, but in general, okay? But in the biomedical domain, you have the difficulty of obtaining data to train and to test, to evaluate, okay? You have to determine types of information to capture. So it's important to know which information you have to collect. For example, diagnosis, treatments, etc. Granularity of information. You have to need to keep in mind the level of detail that you are going to extract and save. If you want to obtain expressive data, it will be the performance to retrieve the information from the database will be decreased, and the other way around. If you have easy access to the database, your expressiveness will decrease. Okay. As I said, heterogeneous formats, no standardized structure of vocabulary or structure. So, for example, in the reports, you are looking for diagnostic findings, and you can find diagnosis, final diagnosis, diagnosis on admission, diagnosis on release, etc. Okay. Different clinical domains: cardiology, radiology, oncology. Lack of standardized domains. So you can, from this part, you can use a vocabulary for each domain. You can have a vocabulary or lexicon for cardiology, other for radiology, other for oncology, other for etc. Okay, but it's difficult to maintain these lexicons. Other way to have the lexicon is to have only one lexicon, only one vocabulary for all domains. But in this case, the ambiguity of the words will increase. Okay. Other challenge is how to interpret the clinical information. These findings, the interpretation of the finding may vary according to the type of report. Compactness of the text. Sometimes the texts are compact, use abbreviations or lack of punctuation marks. You have to keep in mind that the clinicians have a lot of pressure and they don't distract how they write, if they write good or bad the text. Okay. Interpretation depends on the context. There are also rare events, for example, medical error or adverse events that are not always reported. So it's difficult also to have reports with this information in order to train or test your systems. Also, as I said, the typographic and spelling errors. The clinician don't have time to correct their typographic errors, and this could affect your systems. You can lose information or misinterpret it. And also limited availability of electronic records, because not all clinical records are in the electronic form. So we are going to extract information from the biomedical document. We have 10 minutes, so I will run the scripts. Okay. So this is the text that I will use, and first of all, I will segment the sentence as we did before. Okay. So in this case, I use SC Spacey and Spacey and this model. Okay. So I run the code, and as before, as we did in our previous pipeline, we are going to segment the text into sentences. Okay. So if it works.
Can we find on internet like model for UMLS vocabulary or something like that?
In the internet, you can find this the model. This model it's available. Okay.
Okay.
And also you can find the UMLS metathesaurus. Okay, to obtain the information. It's available. Okay.
Okay.
All the tools that I use are available. Okay. No, I used our own tools. Okay. So in this case, I have the text. So the first thing I did is to break the text into sentences. Okay, we have two sentences: myeloid-derived suppressor cells, and they accumulate in tumor-bearing mice. Okay. Once we have the sentence segmented, we apply the name entity recognizer. Okay, and here I detect this is this script. In this case, I load the model, and this I proceed to the NLP to use this model to the text, and then I obtain here with the dot ends the entities. Okay, really easy to use this library, but it's quite slow. So as you can see, I obtained the entities. We have the cells, MDSC, myeloid cells, mice, humans, cancer, hepatocellular carcinoma, and the acronym HCC. Okay? We can obtain the dependencies of the words between the sentence. Okay? For this time, I used a Jupyter notebook, okay, in order to render the solution. So as before, I load the model, I use the model in the text, and obtain the first sentence in this case, okay? And I showed you here these styles is only to show these relations between the words inside the sentence. And this Jupyter is because I use in the Jupyter is to detect if you are using Jupyter or not. Okay, it's not. So here you have the relations of the first sentence. You have the cells is related with suppressor because it's a compound, with derived with a mode, and myeloid with other mode. As you have myeloid derived suppressor cells, and also the backwards and at the right from cells you have the relation apos with MDSC, or subject with, if this is the subject, etc., etc. You have the relation between cells with the other in this case other cells with other words. Okay, and also the activity with cells or with or immunosuppressive. Okay, this is only to know the dependencies of each word in the text. Okay. Also, we can obtain the abbreviations. So we can relate an abbreviation with its form. For example, it's expected that here we can relate HCC abbreviation with hepatocellular carcinoma, or MDSC with myeloid-derived suppressor cells. Okay? So let's see what happens here. It's okay. We have our abbreviation. Okay, I will try to the abbreviation MDSC, and it's related with the definition myeloid-derived suppressor cells, as expected. And HCC is related with hepatocellular carcinoma. So maybe you want to perform a task to disambiguate these abbreviations. So you have this dictionary, and once you have, if you find MDCC, you can change this abbreviation form with its definition. Okay, it's a good idea sometimes to have the definition instead the abbreviation. And also this part of the code is the identify entities and its definition. I will not run it because it takes a lot of time, okay? But here you have the entity is myeloid-derived suppressor cells, okay? This is related with an entity inside the UMLS. And the QE is this one, the identifier is this one, and the definition that appears in the UMLS is this one, is all the definition. Okay. Also, you have other identifiers like twist, and alias is the ways that it can be related. For example, instead of appear myeloid-derived suppressor cell, may appear myeloid-derived suppressor or myeloid-derived suppressor cells, etc. Okay, these are the ways that this name could be appear in the biomedical domain. Okay, and finally the entities, the name entities. I did it using Jupyter. Also, instead is the same text as before. So instead of using the previous, instead of using deep depth style, I used end style. Okay, so it shows you the entities. So you have the entity and the entity name. Cells are cell. MDSC as cell. Myeloid cells as cell. Mice, organisms. Humans, organisms. Cancer, cancer, and hepatocellular carcinoma is also cancer. And HCC, it's a type of cancer. Okay. So here, as you can see, in a hurry, we saw how to extract information from biomedical documents. Okay. So this is all from my side. I don't know if you have any questions, final thoughts.
No.
No?
No.
Okay. So that's
side.
all. As I said before, I will upload the video to the YouTube channel and the slides, and I hope the scripts to the portal. Okay. So thank you for your attention. I hope you enjoy this session. I know it's a lot to process, but I hope you enjoy this session as I do.
Yes, it was nice.
Yeah, very interesting.
Yeah, it was very informative.
So that's all from today. Thank you very much again for your attention. See you guys.
Thank you, Javier.
Thank you.
Bye bye.
Have a good day.
Bye.
Bye.